So let's continue to finish up the last page. We did not finish the last page in last lecture. So we discussed the phase space treatment carefully. And I think that's one of the most important things that you need to be very used to and very familiar with and understand in and out. Because if you see the overall, I think my lectures can be probably categorized as from kinematics to dynamics. So, and I really basically work on kinematic to great detail and trying to make connection, how to uncover the different aspects, the new dynamics, such as physics beyond standard model and so on and so forth. Although I would not describe particular models, what kind of supersymmetry signatures will come into that, but by looking into the kinematics, you trying to understand how you can design things, design the observables, and so on and so forth to dig out certain the signatures. Along the line, when we give examples for the E plus minus collider as well as a hadron collider, you see the connection more and more. So we started on the general kinematic discussions. We said so the first example is the initial state contains the scattering and two particles to fuse into one. And this is an overly constrained system. Two particles will have to satisfy a certain particular constraint with a delta function in it, which basically means that the two initial particles will have to form an on-shell new particle. That's a constraint. First one we did that. And second example is that we say that you can have the standard 2-to-2 scattering, which is the most common processes, simple processes that we usually do. In that case, we discussed the phase space dimensionless, which basically means there's no integration variable as a dimensionful quantity. Therefore, all these dimensionful quantities, such as energy, energies, momenta, are all fixed by the initial kinematics. Two coming in, once you know the initial conditions, and two going out, you know, except the angle. Angle, you have the angular variables, no magnitude. But the third example is that you have a scattering into three particles. And then, therefore, you have 5 total variables and 4 angular variables, 1 energy momentum variable that changes. So therefore, the spectrum is not fixed, and there's a distribution. So then I showed you the phase space distribution. But phase space distribution is a distribution that without putting into the dynamics yet. But the dynamics is weighted by the squared matrix element that it's governed by the underlying interactions and so on and so forth. So that's what we're up to. In general, we'll have these four in this situation with multiple particles. But this is almost sufficient. The reason is that in most of our renormalizable theories, we have 4-point interactions to the most. Unless you want to include the higher dimensional operators. If you include higher dimensional operators, there are more and more particles. Most of the time, we have 4-point particles. So 1 to 3 is quite general already. So it's almost no particular need to go beyond this, unless you have stages. So that's what we want to do. So it's possible to have a stage cascade type of processes. Suppose we have a particle, the initial state particle coming in, and that could be a two-particle fusion in any sense. But then you have a particle 1 going out. Then you have the rest. So then you could continue on. Particle 2 going out. And so then particle on and on. Eventually you reach the last one. Let me see how we write it. So this is the last one, particle n. But before particle n, you have n minus 1. So that's the same as this. And a different way to draw the process. But the phase space is symmetric. It's, no matter how you write it, that's fine. But the only thing is eventually you need to put in the dynamics. The dynamics will distinguish from different configurations. But there is a very important formula. This formula is called the general iteration formula. So this general iteration, or sometimes called a recursion. Okay. So let's use the recursion formula. The recursion formula tells you can, for your convenience, you can break this at any particular point and to write this whole n-body phase space as I give you the expression into two pieces. Into the two-body and the rest n minus 1 body. So there's a formula to do this. You can derive this easily yourself, and that gives you the expression like the n-body phase space is the decomposition into n minus 1 body and times the break up. In principle, you can break it up anywhere, but for convenience, let's just see the last pair. So that is, and this will be the variable. This is the initial state momentum again, and then you have the listing particle 1, particle 2, until particle n minus 1. N minus 1 and n 1 together in this system here. This is the initial state momentum for this pair, but that is the notation I use, this n particle n and n minus 1. This is the momentum for this in the last stage. This last stage serves as the initial state for this pair, but serves as the last particle from the n minus 1 phase space. So that is one part. And then the breaking tells you the second factor is phase space only for 2 body. For these 2 body, start from the initial state, which is n minus 1 and n. This one. This serves as the last particle in this previous phase space, and the parent particle to split into the last pair. So this is the one, and then you have 2 initial state, the final state particles. And somewhere in between, because of dimensionality consideration, there is a invariant mass. Well, there's a mass variable for these 2 particles with a normalization. So there's one more integration. This one is obviously a necessary factor because this particle actually is not necessarily on shell. So this particle is your arbitrary break up. This is arbitrary organization. This is no dynamics yet. This is generically true for any processes, and this is just this kind of identity. You can prove this. So this one is could be any invariant mass. So that M invariant mass of this pair of these 2 systems will define invariant mass in the next 2. So that is general relation. This general relation tells you n-body can be broken up into 2 factors at any place for your convenience, and then integrated over that breaking part for the invariant mass system. So that is the formula. Okay. Therefore, from this treatment, based on our 1, 2, 3 phase space factors, and you can generalize this anywhere in any way to arbitrary number of particles. In fact, this relation is what people usually use. Next time I'll comment briefly about the phase space integration for n-body particles as a Monte Carlo simulation. You can use this kind of formula to generate any numbers to continue on. So therefore, in principle, we not only have the n-body phase space, but we have a particular treatment to optimize your real calculation depending on particular configuration for your dynamical configurations. So that's general formulas. But let me, in particular, this decomposition is most useful if you break this in such a way that this is a real dynamical particle. If that's a real dynamical particle, then this breaking is the most natural and useful. So I will give you the example like what we discussed in one of the homework problems, the top Quark decay. So top Quark decay to a W and a B, but the W decay is really very quick. The W lifetime is also 10 to minus 23-ish. So it's the same order of magnitude because the W mass is also 100 GeV. So the W width is also order for GeV, 2 GeV or so. So therefore, the decay lifetime is also very, very short. You really did not see these two particles. But in fact, the W will decay to the fermion pair. Typically, it's easiest to decay to leptons to show up at the colliders. So let's say it's going to an electron. Okay, this is the top quark, the bottom quark, and this is the positron and missing neutrino. So the top quark discovery was first made for this leptonic decay channel. Okay, leptonic decay channel, you have a B quark, this kind of a B tagged due to the Fermilab Typetron CDF detector to have a B tagging, then very energetic electron and a significant missing neutrino there. So that's the way. In fact, if you look at this process, the really observable here is this B E new 3-body phase space. So therefore, naively, you would have thought this is the process we're going to use, the 3-body. However, this W, because of kinematics, the W is below the top quark and W is on shell. We discussed it yesterday already. That's why this is so big. In fact, if you think of the comparison between the top decay and the B decay, the final stage particles are identical. This is the B to charm an electron. And this is the top to B an electron. The final state actually is the same counting, but why is it so much smaller? We argued already, largely because of off-shell. The off-shell gives you another penalty factor, like the fermion mass, B quark mass divided by the vacuum expectation value. That's G Fermi, vacuum and squared. It's 1/50 squared. So that's the off-shell list. However, that would be the proper treatment. The B quark decay would be treated properly using our the previous discussion, like the beta decay. Beta decay was this example here. This the beta decay. B quark decay would follow very similar to this situation. However, the top quark decay has one intermediate stage. This intermediate stage is largely on shell. So that is a two-step process. So that is the most accurate, but more efficiently described by a top quark decay 3-body into a top quark decay 2-body, which means WB first, and intermediate the propagator mass squared and the final factor phase space 2-body, that is EW. So that is the good treatment. The reason is that if you put in the dynamics, and this one has the W has the on-shell propagator, Brad-Wigner propagator. So that Brad-Wigner propagator has an off-shell distribution, but this is an integration variable. And then we'll come back to this in the next page. So this is the example to tell you that this kind of decomposition is most useful, and to some extent is not even necessary. Okay, so in particular in the narrow width approximation, and this becomes the integration over delta function. So then I will come back to this point in the next page very soon. Okay, so that's the reason. Now, before we move on back to this physical interpretation, let's from this general description for the phase space, let's comment on the simulation so far. So far, we probably most of you and all of you have heard and have tried some kind of simulations using the Monte Carlo method. Right? Monte Carlo method is beneficial for several reasons. Okay, so let me just briefly comment on this and what we do, and not doing anything in particular. So we are doing this multiple dimensional integration. In fact, it's a large number of variables and very tedious and time-consuming calculational procedure. Okay. To the least, not even thinking about other possible variables. In fact, they are, such as the parton distribution functions, which I will comment on, discuss somewhat when we discuss the hadron colliders. You have a 3-particle, 3 of them, and with a delta function constraint. So that's how many dimensions you do. If you think you have a multiple production there, as I mentioned to you, even for 3-body, you have the 5-dimensional integration already. And even more and more. Okay. So if you have had any experience to do numerical integration, you know that when the dimension integration is around 4, then Monte Carlo benefits. Because if you use Gaussian integration and Simpson integration and so on and so forth, one-dimensional integration is not bad. Have a integration over some kind of a function. Okay, you integrate over and get the area as your result, as your I. So that's it. Okay, at I as an integration. But one-dimensional integration, sure, you can use many different methods. Two-dimensional, when this dimension becomes 4, that's the borderline between the rigorous treatment and Monte Carlo. Because Monte Carlo doesn't care about how many dimensions, but the error for the Monte Carlo is always 1 over n squared. Regardless how many dimensions, as long as you shot this one, will be okay. So if you have a large number of dimensions, and then so if for 4 dimensions, and you have 10 shots. 4 dimensions, you have a 10 to the 4th already, 10,000. They think to reach 10 shots in each direction already. But then the error will be huge based on 10 kind of. But if you have 10,000 shots, and the error there is immediately the root of that. It's a percentage also. So that typically is good. In particular, we make this other extreme. Now, if this function is rather smooth, say if this function is flat, you make 1 shot, you get 100% right. So the more flat, okay, the more beneficial the Monte Carlo method would be. Okay, so that's the first reason that Monte Carlo actually benefits when you have a large number of variables, and which is very true for most of our simulations, for physical processes most of the time. So the second reason is that the Monte Carlo simulation is very, very close to our real simulation. It's very close to the real simulation because we do experiments. There's one event, and this one event is characterized by the momentum in that direction and with the such measurements. And our Monte Carlo generation, based on this integration here, indeed start from the variable integration to give you particular angle and particular magnitude size. That's the direct analog to real events. So therefore, our Monte Carlo method is not only a method, it's a real simulation to the real processes. So that's another reason to beneficial. Okay, so that's why we want to go with the Monte Carlo method. Most of you must have some experience there already. So the integration here is simply random shots. You take the random shots to evaluate this function at any random shots. You take the shots as many as you can afford, and you average over this how many evaluations you do, and then of course you divide you multiply the overall volume, which is the Jacobian. This is Jacobian that when we change this x into from 0 to 1, right? I showed you every step when I do the phase space, I derive this for the variable from 0 to 1, so that you do the random numbers xi from 0 to 1, and the volume over there is a Jacobian factor, 2 pi times 2 and the 4 pi and so on and so forth angle, and the momentum from minimum to maximum. You pull out all this is the real value. So that's basically it. The error is statistical, 1 over n squared. So that's typically the case. So as I said, the more flat this integration function is, more accurate this will give you. Okay, so that's a good thing. However, many times in our real physical processes, when we put into the dynamics the squared matrix element, it's not very flat. So far, everything is very flat. We are only dealing with the phase space, but a squared matrix element would not be very, very flat. Sometimes it can be as bad as this. This integration variable for the off-shell W is not flat at all, like this. If you take 10 shots, most of the time you miss it. That's very, very bad, very, very bad estimate. Right? So the Monte Carlo will be very, very bad. So what do you do? Then, so far, there are techniques in dealing with that. It's called important sampling. So I only tell you, but I will not derive anything. So that the Vegas is the powerful simulation package that many of you must have used. This by Peter Lepage. And he took this approach. The first set, he would calculate these random shots, and a few of them land somewhere a little bit higher than the others. And you won't be lucky to hit the top there. And then the program would keep this the sampling, would keep the sampling where you put the shots and how large the rate is. And next time, when the Monte Carlo starts the second iteration, it weighted towards that. So the larger cross-section region will throw in more shots and take more shots in this region. This one is big in this region. Fewer shots here. And next time, the next iteration is here cross-section is bigger. And every iteration is trying to keep that. It's called important sampling method. In fact, nowadays, the method has been a lot more sophisticated. This is the idea. But now the real implementation has been a lot more sophisticated than this. Like if you run MATLAB, and MATLAB is very smart to adjust the function. The adjust function not only for this resonance. We used to have the resonance only, but now we have multiple particles, splitting and collinear, and many times the variable may have this singularity, PT singularity or something. And so nowadays all these kind of singularities have been identified to multiple processes and have had some data samplings towards these things. So the simulation, the Monte Carlo simulation, is the way beyond the simplest throwing in the uniform dice. Now it's rather to gauge towards the functions. So the MATLAB has this also. They even publish a particular paper. We tell you how to optimize these. Nowadays, the package is very, very efficient. But the idea is like this. We use random number generator to simulate the events, to calculate the particular momenta, energy, momenta, angular variables, and then weight it to the real physical process. So finally, just before we move on to the real, so that's more or less I want to tell you how the phase space is simulated. And so there are two kind of events. The events we are talking about here is that once you generate the particular random number point, you calculate the squared matrix element for this process, and of course the process tells you there is a Wegener propagator, and then you calculate that one, and that's the weight. That's the weight for that particular phase space configuration, phase space point. But in the real world, it's not the case. Real world, and when you do the LHC experiment, and you find a W event, you find one, right? So the event would not tell you this one has a larger weight. Okay, so you do not know that event. You have one event, and next time you find another event, which may or may not be W event, maybe your background, and so on and so forth. So in the real world, you continue on to collect a larger amount of data. You find many, many more events in that region. But each event carries one. Does not carry the squared matrix element you calculate. So the squared matrix element you calculate is called weighted events you generate. And the experimental counting is called unweighted event. Each event is weighted by one. Okay. So it's unweighted. But you count more. Experiments, you eventually you have same distribution. But the experiment has many, many more events. Each event count one. Okay, so that's the distribution. Here, for your theoretical calculation, you calculate one shot. You kind of calculate one shot for every configuration, but each shot is calculated according to the dynamics to tell you how big that is. And eventually, distribution should fit, should the same. Your theory described the phenomenon correctly. So that one is called. Most of the time, our Monte Carlo generator is start from weighted events. And the real experiment collect unweighted event. There's a way to treat this both. There's a way to generate uneven event as well. But I want to tell you the overall simulation difference and so on and so forth. Because of time, that's more or less all I want to tell you. The phase space treatment and the phase space optimization, the Monte Carlo approach. Okay. So now let's come back to this the top quark decay give you the further example along this line. Okay, so let's look at this process again. So using this thing and also illustrate some possible phase space treatment or some integration treatment. So remember this, that the flatter the distribution is, the better estimate the smaller error bars that you would obtain for the Monte Carlo approach. The more singular distributions, the more difficult the Monte Carlo approach will lead you to correct result. Now let's consider this top quark decay type of things. Okay, in general, let's consider a heavy particle. In fact, my example is top quark. I want to make this general, and to decay into a particle A and B, and this B actually is a particle B, but not necessarily the bottom quark is same notation happen to be, and another intermediate particle. But this intermediate particle will split into two particles, momentum P1 and momentum P2. So because of the decomposition formula for one particle to 3, to make that into a two-body and an intermediate off-shell particle, and you have an integration over the intermediate mass. And that is this intermediate mass integration. But kinematically, the integration has a maximum and minimum. Okay, the maximum integration here corresponds to the mass difference. So the available mass will be the parent mass, subtract out the final state single particle mass squared. That's the upper limit. And the lower limit is that you have to produce the two particles. So this is the lowest the mass variable you need to reach so that you can this virtual particle will split into two particles to the minimal mass energy. So that integration goes from the minimum to the maximum. Maximum is available, how much energy available to begin with, and take out this the other cost, the particle B. So that's the thing with you. However, this integration is usually attached with this Breit-Wigner for this virtual particle, which is only useful when there is a Breit-Wigner. If there's no Breit-Wigner particle, and this decomposition is just a formality. So it's an identity. When there's an intermediate particle with a particular concentration in this Breit-Wigner or delta function, and this decomposition is most useful. So if there's a Breit-Wigner form like this, particle width, vertical particle. So this is the numerator. Sorry, there must be another one. So this is the Breit-Wigner resonance formula for the relativistic situation, and for that one. So this one is very peaked in the Breit-Wigner region, and it has a delta function representation when this width is very, very narrow, whether the width is very, very narrow, right? We discussed about that. And that is the situation like this. But then, obviously, this integration is very, very difficult to calculate if you simply use the uniform random number calculation like we described there. And how many shots you have to throw in to effectively hit the peak region. So you may consider variable change. Okay, this variable change, this kind of variable change is implemented in different packages, not all over, not everywhere. But this is the thing that when you do the calculation, you may consider to do the change yourself. So it so turned out this is a rather easy treatment. Let's define an angle. But you can see this has some trigonometry relations here. So the trigonometry correspondence to that. Let's design a tangent to be the first variable, first factor, first term. So this is the first term. You define this with tangent beta, and then you find this is the variable, and you make the theta variable. So in that case, you find the variable mass integration is converted into a variable integration over the angle. So that becomes one observation here. And then you see that the downstairs there, you find that it once again becomes another relation. It's gamma v square. There's a square there too. So then you substitute all these things together, and you find this integration over the mass variable modulated by the singular Brad-Wigner behavior. It's smoothed out. If you use the integration variable theta, and you use the theta from 0 to 1, from the maximum to and minimum, I can write down the maximum minimum here as well. So in fact, the maximum minimum gives like a theta maximum from that argument is arc tangent 1, 2, minus intermediate, and theta minimum is arc tangent MA minus MB, all coming from our previous calculation. So in fact, the maximum in the limiting case, narrow width case, and these go to minus pi, and these go to 0 in the narrow width case, in limiting case. So now the good thing is that this variable, after this transformation, you pick up a Jacobian factor to give the volume. This distribution is flat. Again, I gave you the example already. You put even through one shot, you get 100% right. So this is the way that you want to treat your own calculation to make this integration more smooth, so that your Monte Carlo will be extremely efficient. If you ever try this, you should try this just for yourself. You try this to see the Brad-Wigner. It's very hard to map out the Brad-Wigner, how frequent you can really have the chance to hit there. Very hard. Once you do this, you do the calculation, the analytical calculation, convert this back, you get this really very efficient to get this correct. So this is the one way to do that. So in fact, this tells you that in that limiting case, this Brad-Wigner will convert into the, in the limiting case, it will convert into the delta function. That's once again the narrow width approximation. Okay. So the narrow width approximation is to make this Brad-Wigner into on-shell particle. You put an intermediate particle on mass shell. Okay. That actually eventually gives you. In fact, I intend to write this as homework, but I did not get a chance. So that one would that calculation put into this particular situation would make this W a narrow width on-shell W. So the calculation here is that the partial width for the top decay to virtual arbitrary W with the Brad-Wigner B finally into B this width calculation. You do this proper phase space treatment, you find that is equal to the decay W on-shell B on-shell and times the branching fraction for the W on-shell to electron U. This is a common conclusion that everybody uses. Okay. Naively, you say that what is a top decay branching to electron? That basically means that you do the standard top decay to B and W, simply multiply the fraction for the W decay. That is obtained by that integration treatment, so that you set the integration as a narrow width, and you put the most important contribution part here is essentially delta function for the W, and therefore you basically have a two-body decay. This is really a two-body decay. One is from the two-body decay here. One is the other two-body decay. W2 electron nu divided by the W width. There's a W width downstairs. That's where the normalization comes in to give the branching fraction. Okay, so that will 1 over the W width is the 1 here, and then so you get the branching fraction. Okay, so that happens quite common. Pretty much any time if you have an intermediate but nearly unshelled particle, and the numerical results, it's not counting the angular distribution and so on and so forth, the spin, in particular spin correlation and so on and so forth. If you ignore the spin correlations for the distributions, only think about the rate, it is simply multiply the branching fraction for the intermediate unshelled particle. You have a question?
No, it was about the spin correlation.
Yeah, spin correlation, the total rate here, I did not comment on. But of course, if you want to see the angular distribution and so on and so forth, and Michael discussed this already, the left-handed W would give you certain preference for the leptonic final state, and right-hand W would give you opposite. So this spin correlation certainly should be built in, but that would not affect your total rate. Total integrated rate would remain like this.
So do you have a way to quantify how much these spin correlations contribute or not? Because for the narrow rate approximation, we can more or less see.
The spin correlation does not change the rate at all. The total rate gives the correct one. You average over you sum over them, average them already. The only thing is that if you want to see the differential distribution, then you want to, for example, you want to see you are not happy with the total decay. This is exact. There's no approximation.
The formula is exact.
Yeah. So after you're summing over all the spin, averaging over spin, and so on and so forth, that would show up. Okay, but you sum over and averaging over spin. This is the correct. However, if you want to look into the spin correlation, you are thinking the possible d cosine theta for the electron. So you are thinking the electron distribution. Then you are thinking that the intermediate W would decay to an electron this way or that way. This formula is the result integrated over. But if you want to see the differential before the integration, then of course it has shape. That's what we're talking about. This is called the spin correlation. It's correlated.
But then I'm a bit confused, because just by looking at the left-hand side of that equation and the right-hand side, so that W, let's say, has some helicity or some polarization or whatever.
Right.
But on the right, the W that goes inside the width and inside of the branching ratio are completely independent. So whereas on the left-hand side, it's the same. It's exactly the same particle, so it will have the same spin. But on the right-hand side, there's contributions coming from. Those
here,
aren't related, right?
Here is a calculation summing over all spins already, right? Here is a calculation summing over all spins already. Right. In principle, they are correlated. However, each orthogonal, here we have 3 states. The transverse polarized, the transverse polarized plus minus, longitudinal polarized 1, they don't interfere in the particular frame. So each one of them is squared. So the interference actually cancels out. The total rate works out okay. But distribution, not. Distribution, you need to keep track. So if you only care about the total rate, they average out. Yeah, total rate works okay. Yeah, in principle, sure. In particular calculation, you should carry through the correlation. You should carry through the propagator. That's the propagator does for you. That's the Brett-Wigner propagator. You have this Brett-Wigner propagator here. When you do the calculation, before you square that, it's this one non-squared with I, right? And then that one has something like a G mu nu in it. G mu nu connect one W with one index and the final state W with another, and that's where the correlation in principle comes in. But I did not calculate the field theory elements. That's I told you that I skip field theory parts, but only give you the features. So that's the feature state. Okay, so I think that's as much I want to discuss about the phase space treatment. You see that the phase space treatment is pretty rich. It's many things you should be familiar with and be creative in playing with the new physics search and so on and so forth. Okay, let's move to the observation aspect. This is my chapter 4, and hopefully chapter 4 will be rather short. So this is about the particle detection. As I mentioned to you that as a theorist, you deal all these particles as individual particles, and you think they are all elementary particles, stable, long-lived, and on mass shell, everything seems to be idealistic. However, in reality, you should know certain things if you want to carry through your phenomenological analysis or phenomenological ideas. So that's some basic knowledge we should know. Particle detection. But particle detection in particular at a collider environment. The collider detectors. That's rather modern, in fact. Those are the technological developments, relatively modern, only until maybe 20, 30 years ago or so. It's gradually developed further and further. It has been improved. It's being improved further and further at any time. So the upgrades, the detector upgrades for at the CMS, and every time they upgrade, they have a new component to do the particle detection better. It's very, very impressive. So it's somewhat even hard for us to come up. On the other hand, we also contribute. We tell our experimental colleagues what physics we want to see. You should be able to tell us the B by tagging. You should be able to tell us the kinematic region in this forward region or something. We, as a theorist, as phenomenologists, also suggest what kind of new physics we're looking for, and you probably should help us to design, improve your detector, and dig out the physics we need. So that's, once again, this the two-way traffic between theorists, particular phenomenologists like us, and our experimental colleagues, and back and forth. So let's have some basic idea about these detectors. So how we see the particles? Of course, it's not like I told you that's real, that Rutherford experiment, and he really had his colleagues, I don't know, it's a graduate students, but his colleagues to count the shots at the different regions. So that's how you do. But nowadays, it's impossible, right? Not only for these, our naked eyes are not sensitive to see things, and secondly, this is so fast and so many events that that's just you have to digitize. You have to use the electronics to record, to tape the events on and analyze. So that's why the particles we discuss here is only some objects in their detector registration rather than electron as we think, in the muon as we think. So some general features you want to know. So how do we see the particle? All the particles in the standard model behave very different. Most of the particles behave very different in the real world once they are produced. The top quark will immediately decay, as we discussed yesterday. The bottom quark will decay much later and much more slowly and behaves like long-lived particles a little bit. So the first thing we want to estimate is long-lived, short-lived. Whether these particles behave like itself or that represents into a bunch of final states immediately. So the how long this particle lives, how far this particle travel within our detector is essentially a central issue. Okay. So first of all, let's think about the travel distance for a particle. So travel distance is the particles are typically the relativistic. Okay. So beta is the velocity, but in units of c. But beta c is the real velocity in our normal units, not in the natural units. So that typically would be in units of meters, centimeters, or something already. But this is the units of 1. C is 1. But this is the distance. But then how long this particle lives? That's a proper lifetime. Proper lifetime means the lifetime, but when the particle is at rest. Okay. But then this particle will have a Lorentz boost, the gamma factor, the Lorentz factor boost, as we discussed yesterday. Also, the faster this particle is, the relative boost factor in between our lab frame, your detector frame, and production frame for this one will be enhanced. Okay, so that's basically how observation is sitting at your detector measurement, how this the particle will travel. So that's typically that one. But let's normalize the C and into some detector size. Detector typically is 30 meters, but the resolution is the key thing. How short a distance that a detector will be able to tell us there's a particle showing up, there's a particle propagating. So that's about microns. So, okay, so microns is typically the size. So we normalize these two. So that's approximately convenient thing is 300 microns. And the tau and your gamma factor. This gamma factor can be large. So 1 is slow, non-relativistic. 10 is possible, even larger than 10. 100 is also possible, depending on how fast this particle is moving. Okay, so that's the tau. But not the sensitive number here is what is the normalization to measure this tau to make this almost like 300 microns. That is resolvable, typically resolvable. In fact, the resolution is better than that. Resolution is 10 microns or so, typically. It may be slightly better. I mentioned to you that every time when Atlas CMS upgrade their silicon detector, they improve this. I think it's the order of 10 microns or so. So that's what they can resolve. And this is a decent number. And so turn out that number is 10 to minus 12 second. Which means if the particle lifetime is order of 10 to minus 12, that's an important number, remember this. Okay, if the particle lifetime is order of 10 to minus 12 second, and if the boost factor is order bigger than 1, 10 or 10 years or so, so this particle will propagate in your detector order of microns, so maybe even millimeters, microns, 10 in that way, maybe even centimeters. But if it's much longer lived, it will propagate even further, meters. Okay, if this is even much longer lived, they behave even more different. Therefore, this is a dividing quantity. How the particle will behave will be observed in our detector environment. So remember this 10 to the minus 12. Remember what is a 10 to the minus 12? Last night we discussed B quark lifetime. That's why B quark and charm quark is so critically important. They are right in the borderline. If your detector is good enough, you see the quark, the bottom quark propagate somewhere within this resolvable range, and suddenly it decays. It B meson decays. So we call that tag, B tagged. It's B. Not like others. Others like a gluon. Immediately hadronize, bunch of particles go along, no resolution. Like top quark, immediately decays, no resolution. So therefore, this is the dividing quantity. We have to discuss all different particles based on this general argument, how you see that, how that behaves in your detectors. Okay, so that is a general discussion. Now let's list. Let's list those particles according to the lifetime and travel distance as the important behavior to categorize them. Would be the best if the particle is stable. Never change the identity. So that's great. It's everywhere. So from the production to the end and everywhere. How many of them? particles. When we know electrons, we know protons. That's about it. Well, sometimes you have high energy photons. So that's about it. So those particles, they're absolutely stable both in our theory and in our observation. We haven't seen proton decay. I think it's more traditional to say proton and antiproton, rather than notation-wise these days we call it antiproton rather than P plus minus. Okay, so that's about it. However, there are many other particles seemingly behaving like this. There's a quasi. So quasi-stable particles means they actually are unstable, but in the collider detector environment, they are long-lived enough with respect to that. Much, much longer than that, it propagates all the way. Meters, 100 meters, it goes out of detector. So within your detector components, they seem to be long-lived. So there are many of the particles like that. So typically, if the lifetime is order for 10 to the 10 to minus 10 seconds, then with a gamma factor there, it goes like meters and so on and so forth. If that's the case, the particles behave like a real particle through all the detector. Then of course you have many neutrons. Neutrons lifetime minutes. Okay, so things like this, a few minutes, and some hadrons, k long, and muons, microsecond, 10 to minus 6. So lifetime 10 to minus 6 rather than 10 to minus 10, even longer lived. Muons are always, muons is the best particle, most best behaved particle. Long-lived, almost like a long-lived particle, very massive, moving slowly, and all the way, it does not interact with many other things, it goes all the way to the end. So muons is the best. If you have your new physics signature to give you muons in the final state, you make your experimental friends very, very happy. So this is the muons really, really good. Pions, somewhere in between, certainly the lifetimes are long enough. It's because they weak decay. So we discussed it's already only decay to muons too, so on and so forth. And charged kaons. A few of them, not all of them, some of them, those guys would be long-lived in the same observational aspect, like those. So that's something between. Then we comment already, somewhere between the borderline. At the borderline, the lifetime with a tau order for 10 to minus 12 in that region, then they displace travel, but then they decay. So that's very characteristic and very, very interesting, very, very important. So this is a particularly important displace. So they display a secondary decay vertex. It propagates to a notable resolvable distance, and then that time, at the end of the lifetime, and then decays into some other final state, direct observable and long-lived particles. So that's one. So as we mentioned already yesterday, B mesons, because B quark lifetime. So this is basically B quark lifetime. Of course, we cannot say B quark lifetime. B quark never exists as a identifiable separate particle because of the QCD hybridization. But B mesons is dominated by the B quark decay property. I mentioned to you that they have the quark effective field theory and so on and so forth, justify this to a good approximation. Similar for the charm. In fact, I should have made this as a homework assignment as well. So why not compare with the charm? Why charm is so much lighter than B? Why is the charm quark lifetime is not 10 orders of magnitude shorter, same order of magnitude? Charm quark decay, charm meson decay is somewhat close, it's in the same order of magnitude range with the bottom quark range. Instead of seeing C, again, it's the mesons, D mesons, and tau somewhat shorter, but It's similar. So those are the set of particles. B-flavored hadrons, charm-flavored hadrons, and tau are more or less in this range of border lines. In fact, so far, observationally at the LIC, all of these kind of particles have been identified associated with the secondary vertex detection. This is part of powerful identification called the vertex detection. It's a particular piece of instrument. It only developed not long ago. Its first one implementation was at the Fermilab Tevatron for the top quark discovery. This was only in the early 90s. You have a question?
Yes, I wanted to ask about the tau lepton, whether it's possible to measure the decay vertex, because this is kind of important in the Higgs CP determination.
Yeah, absolutely. So the measurements and observation has been made already, but it's not very efficient, because you demand. So there's always a distribution. Right? Even I gave you the distribution, the exponential decay. We said a lifetime that it's not a sharp decay. Now it's all leaves, and suddenly it's all tau is gone. It's not like that. So the distribution and how efficient you can pick up, how long you want to wait, how short you want to cut. So it's always an optimization process. Its efficiency is pretty low. I think I had a few numbers at the Hadron Collider. I think tau, the detection efficiency probably is around 30% or so, 30%, if I remember right. It may be updated. B quark efficiency is extremely impressive these days. At Fermilab, it's only 50%-ish, or maybe slightly lower. If they were doing the B tagging efficiency as much as now, they would have found a Higgs. So this it's very, very marginal for the Higgs. At the Tevatron, it's another interesting story. Unfortunately, we don't have time to discuss. The leading channel for the Higgs discovery is a Higgs BB at the Tevatron, because of background, because of singular rate and the background. But the leading channel at the Higgs BB channel at the LIC is completely swamped by the background. So if they were able to improve the B tagging as good as nowadays at the LIC, they would have been able to dig out the signal. So the B tagging efficiency nowadays is almost 70%, and charm is 50%, tau is slightly worse, but depends on your requirements. So that's very important. I think people are working and pushing for that. Certainly, yeah. So that's the somewhere in between. However, there are many other shorter-lived particles. And unfortunately, these short-lived particles would not directly seen themselves. But it doesn't mean we cannot identify. Like top decays yoctosecond. Okay, so that's it's not going to behave like a particle itself. However, we reconstruct that from the decay product. So not directly seen by this, but reconstructible. Examples includes pi-0 electromagnetic decay. It's rather fast. Electromagnetic, I think 10 to minus 14, 15-ish, but quick enough to see that. And other things like rho. So then those particles would not appear as they are themselves in your detector. Rather, they become something else. You may reconstruct, you may not reconstruct, but what you see is already found decay products showing up. Similarly, important ones, WNZ. It's also the lifetime 10 to minus 23 in that region, lifetime, very, very short, immediately. So you will not really they see a WNZ in your detector sense for that. And top quark, as I mentioned, and Higgs as well. All these new heavy particles, largely because of mass in the available phase space. So that's a part of the reason. The larger the phase space available, the faster these things will decay. So they decay real fast, very short. Then you only can reconstruct them. So that's the way. finally, there's another group of particles. You never do anything like neutrinos. It's just weakly interacting, missing. Our so far detector technology can only detect interactions with the detectors for the electromagnetic interaction and hadronic in the strong interactions. The weak interactions that we don't have detector. The only one, I would say the only one would be the S cube for neutrino telescope. Yeah, I would say that's probably the only one. Super K probably not. Super K still look for the charged particles, if I remember right. Yeah, so it's only the neutrino detector is huge. So a few events you can see. So far there's no conceivable method to really detect weakly interacting particles. So therefore, the particles like purely weakly interacting would be missing particles, such as neutrinos, such as neutralinos. That's our dark matter candidate in supersymmetry, and such as maybe gravitinos if light gravitinos exist in our supersymmetric formulation or something. There's a question. Yes.
Can you say whether B meson, for example, neutral have the same decay time, but for the pion it's totally different? You understand what I mean? So
I didn't understand.
We have the same time range, like 10 to the minus 12, you said.
Right.
But for the pion, you have for the charged ones, they are long-lived.
Yeah.
And the neutral is short-lived.
Neutrals, yeah, neutral. This is a weak interaction. This is from the pion through a W type to a muon, electron, and neutrinos. This is the weak interaction. And the pion, this is the pi plus minus. And the pion here is through the anomaly electromagnetic interaction. So this is electromagnetic interaction, and it's stronger than the weak interaction. Is that the question you're asking?
Yeah. And with the B meson.
B meson is similar to this, but the three-body decay. Three-body decay is a little bit slower. Yeah. Mm-hmm. But the difference between this and this is largely because of the quark mixing. So this one, I mentioned to you yesterday, the VCB is additional suppression factor by 10 to the minus 2 or 3, remember. And this one is a VCD, VCD. It's much, much smaller, 10 to the minus 5, and you square that. So that's why you make this very, very, very small. Yeah, so the same order. If you count it, the 3 factors I mentioned there, it so happened to come back. It's interesting. Okay, so that's about it. So now let's see the some detector components to pick up those features. Okay. Those features will come into different components. Okay. So this is a general modern setting of the detector layout. Okay, the top one is essentially a kind of a cylindrical. This is the cross-section cut. Okay, that is the particle beams. Let's think about LIC. For LIC, you have a proton and proton coming from both ways and interact in the middle. And this is a cylindrical thing because the beam is cylindrical. So therefore, your detector should make the similar symmetric shape. So it's a cylindrical shape like this. So this is a cross section. So this is a central region. Then you have this magnetic field in the central region so that you can bend the charged particles. You know those are charged particles to pick up the charge. And further inside, you have a very fine resolution materials called the silicon vertex detector. That's where it is very sensitive to the chart the track and have a resolution to tell the so-called the second vertex. So that's one of the important. There are several different ways to do the so-called B charm identification. The most common, most interesting one that I want to comment on is a secondary decay by this vertex detector. So that's only this piece. So that's the second piece. And outside this, the magnetic field, you have the electromagnetic calorimeter that absorb electromagnetic showers. Electrons will be absorbed there. Photons will convert into the electromagnetic shower and so on, so will be absorbed there. So that's what it's a calorimeter. It's measured energy. Okay, so that's where. And then further outside, neutrons in the some of the K long kind of strongly interacting. They don't deposit much energy because they are very massive. They don't deposit much electromagnetic energy into this the electromagnetic calorimeter. They will go further. They go further out, then you have a very heavy element like lead or other things to absorb the hadrons. It's also energy absorption. It's a calorimeter to absorb the strongly interacting particles such as the neutrons and the K longs and lambdas and so on and so forth. So that's an outer layer hadronic calorimeter. So that's it. But far outside is what I mentioned, muons. Muons rather heavy. They would not radiate too much. Therefore, they would not be absorbed, not lose too much energy in your electromagnetic calorimeter. They would not participate in the strong QCD interaction and would be not be absorbed by the hadronic calorimeter. It goes all the way out. Any new physics like the fourth generation heavy leptons, long-lived, or any other in your theory, may behave like this. Heavy leptonic charged particle would behave like muon. Would not deposit energy in the electromagnetic radiation, would not deposit energy in the QCD absorption. It goes out. Charge tract goes out. So that's the muons. Outside this muon chamber. Outside most of muon chamber. So that's the general setting. Trying to catch all these the features. Now you see the physics come into the implementation, and that's how the real design would have to do in order to catch up all these things. You have to understand these things first like this, and then you see how you can do that and not miss any. So that's the thing. Now let's look at the other diagram. Sorry, it's rather low. Can you see from far back there? So this one is the same meaning for that, but decomposed into the layers. Okay. So first of all, tracking chamber. You see the track, the charged particle in the strong magnetic field to see the bending. Okay. Then this electromagnetic shower will absorb photons into the electromagnetic showering. Electrons continue to shower, but electrons certainly will leave a track at there, but photons will not, the neutral. And the muons will leave the track, and also does very little, and hit into your muon chamber there. So the muons will the only one to go all the way. The hadrons would go through, because they are massive, they won't deposit much energy here. They do have a little bit, but not very much, and continue on, and then this the material would absorb this strong interaction. So that's the heavy particles like neutrons and protons. Neutrons would have no track, also deposit energy here. So if you are able to see all the components, more or less you can do something, but most of the time you won't be able to have all the information. But this is only the illustration for that. But let's go a little bit further. So this is the same, once again, same thing, but it gives you the same idea where the hadrons will end up being, where the muons will have a being, but usually they have the track. Depending on whether the magnetic field is there or not, certain things will not, the photons will not, in the hadrons, neutral hadron will not, but this is just illustration. Typically that's the event shape. When you take a record, you record the events there. So that's the basic, yeah. The important lesson for theorists we want to know is the following. So how would you measure we calculate energy momentum. In my formula, I only know there's a muon with a momentum distribution such as. That's all we do, right? So then you have to tell us not only muon, but tell us the momentum or energy, something, and the angular distribution. That's what we have done with the phase space. We have angular distribution for particular particle location. We want to know the particle content. We want to know the momentum in our description. So how do you convert this into your measurements from this observation there? So that's the next stage. For the charged particles, we measure the curvature. You measure a few points. it has a huge hit on your electromagnetic, on your electronic wires. You set up electronic wires, and you have a few hits. Then that's how you measure this. You measure the curvature for the charged particles to determine what? Determine momentum. So the classical E&M tells you that the curvature has something to do with the momentum, right? So so charged particle, you have the curvature to be proportional to the charge and proportional to magnetic field, but inversely proportional to the radius. Okay, so that's the curvature and the relation between the curvature and the radius. So you can decide that. But of course, the radius here, let's put it this way, it's proportional, inversely proportional to the radius, but the radius is given by the momentum magnitude. This is basically velocity. So this is classical E&M, and the velocity times mass. But in fact, more accurately is really the momentum. It's give you that. So therefore, you measure the curvature, you measure the momentum. So that's where you measure that. The error bar for the momentum determination, you take the derivative and change the error bar on the curvature. Curvature is where you measure, and your error bar is the curvature determination, right? So this the K there. So that actually is proportional to P. So intuitively, it's also understandable. If you carry out this few steps, you find it. It's intuitively understandable. And as a more energetic particle, be faster and flatter, right? So less different curvature than that. Okay. So the faster, it's more difficult to, if this is the band sufficiently, lower momentum, it will be band sufficiently, then it's easier to determine the curvature. But a more energetic one is more difficult to discard the curvature. Therefore, the error on the momentum determination is worse and worse in terms of the momentum. So that's the charged particle measurements. But the electromagnetic and hadronic particles would not show very clear curvature. Is not best to measure that one. For example, the photons. Photons would deposit energy in the electromagnetic calorimeter in this region. It interacts with the material. It's a showering off with many more particles like a shower, and then each piece will be absorbed by the system. So therefore, this is almost like a random scattering process. This is statistical. The more particles you measure in that place, the more accurate you determine the energy. So the more energetic particle will give you more showering particles, the better estimate you will have. So therefore, in this the E and M, as well as they call the ECAL. ECAL is electromagnetic calorimetry, or HCAL, hadronic calorimetry. In that case, you collect the energy deposits by the individual hits. The more hits you have, the more accurate statistic you have. So therefore, you don't measure the momentum. You use the calorimetry to collect energy. So that one gives you the statistical estimate. That's something basically we should know, theoretically you more or less know. The more energetic particles for the electron, so therefore electron and muon behave very, very differently. So measurement is very different. In our standard model, electron, muon, universal, they are identical. No, they are measured in a very different components. So the accuracy, the more energetic electron, you have a better relative error to determine that. And the more energetic muon, no, you get worse. And if the muon is so energetic at the TeV, you can even have a hard time to tell this mu plus, mu minus, because it's almost very straight. So to some extent, when you think about new physics, and those connections should come to mind from time to time to make the study more relevant. So that's the thing. So typically, the resolution would be with additional pre-coefficient like 10%. For ECAL, then order for 50% for edge count with the coefficient on top of that, and then the scale with energy like this. So that's a typical the components like that. For the final, not final, the next important feature will be the vertexing. Vertexing, can I do this rather quick? Yeah, let me just quickly comment on that. So this is the one that next figure. Okay, so this is the one that we are able to resolve the travel because of the relatively long lifetime for certain particles, such as the heavy quark mesons, B meson, charm meson, and tau. They propagate long enough. They propagate long enough from this primary production vertex. This is the place the BB bar is produced by gluon fusion or largely by gluon fusion. But once they produce, before the B quark, like top quark, to decay, and the QC interaction sets in at 10 to minus 22 second in that region, 23 second in that region, and then this B quark forms the B meson. But the lifetime is rather long. If the B meson altogether form this one, it moves to some distance, almost like microns. In fact, the resolution so far, I think it's not even so far, it's better than that. I think when the LHC started, the resolution to resolve this secondary vertex, the secondary vertex is where it particle decays. But the reason you can do the second vertex is that suddenly it decays to some charged tracks. Okay, but those charged tracks eventually you can keep track back them. You find they don't go back to the primary vertex. If you have two charged tracks, you can track this thing back. They meet here, so displaced from the primary production vertex. So that's called a displaced vertex. So that resolution is roughly about microns. In fact, 30 to 50 microns. I think now it's better than that. This is some typical numbers when they discuss the intensively back and forth in their TDR technical design report and so on and so forth, all online. But nowadays, when they improve these, they only publish these in one of the papers. So it's hard to keep precise track. But of course, you go to the web page, you can find it. I think it's somewhat better than this, slightly better than this, but not order magnitude better. It's maybe factor less than factor 2 better. So it's slightly improved. In the order magnitude, this order magnitude is basically red, 20, 30 microns that you will be able to. Then also applicable to new physics you're thinking, right? If you're thinking about new physics with the long-lived the heavy quark, long-lived the charged lepton, if the lifetime is this order magnitude, you can consider to take advantage of this kind of search and so on and so forth. So that's roughly about that. And the technical efficiency so far is pretty good for B to use this kind of separation. So it's impressive. You can tell the B apart from other light quarks, from string quark or string quark with a bunch of hadrons immediately, and U quark, D quark, and gluon, light quarks, we call them jets, right? It's very energetic. It fragmenting into many gluons and finalize into the hadrons. A bunch of them going to the same direction. A bunch of particles, we call them jets. But B quark behaves slightly differently, much nicer. So B quark tagging is highly efficient. And charm is not very good yet. I think charm is something around 40, 50-ish. I don't think it has improved much better. Tau is also done. Tau, it helped a lot for top quarks for the Higgs search. Higgs to tau has been identified. Higgs to tau channel has been way over 5 sigma already. So it's conformed. It exists already. So that's because of the efficient tau tagging. I think it's only about 30 to 30% also. So that's the current situation. For our phenomenological calculations, what you can do is you do our previous calculation for phase space generation and matrix element, and maybe toss in a fast factor, say 30% times this 30% to say this is my estimate the tau signal yield if I trust your efficiency. So those numbers, some numbers we can adopt to use, unless you want to do a more sophisticated simulations to run your experimental simulation packages, which happens these days. It's a kind of convenient available. Okay. So finally, the short-lived the short-lived particles, as I mentioned here, you can do the reconstruction, right? As I mentioned to you already, like short-lived. Z, you can reconstruct this from E plus minus, and all the particles will have to come and behave like this. Those are observables, no matter what. No matter how fancy the particles are, that's all. That's all. That's all available to you. Okay. So the Higgs, go back to look for the Higgs from there. Okay. So that's all you can do. You don't see Higgs. Z is the easiest. Very sharp peak. Only a few events. In fact, the W cross section is probably bigger. That's the reason. W will decay to mu plus minus. Neutrino, E plus minus, neutrino, and the W production is larger because of the charge current, and also the parton luminosity is slightly bigger, including the decay branching. The decay branching to the one charged lepton channel is almost 10%, 9% or so for that one. And the Z to one lepton pair is only 3%. So you count the branching lower for the Z and smaller cross section. Therefore, W is order of magnitude larger yield than Z. So W was discovered first, but the Z was discovered pretty soon, within a year or so, at the CERN at PP bar S. But in that case, when they discover the W, they find the Z is reconstructed by the invariant mass near the Jacobian peak. See these very, very sharp. For W, as I mentioned to you, there's only one, and that was distribution like this. This is, you only look for the only one particle, the charged lepton. So that's also the peak from the one that hopefully I would discuss this quite a bit for the kinematics. Okay, so that's from reconstruction and the Higgs, of course, from final state. The discovery channel, interestingly, is from Higgs to gamma gamma. It's not because the branching fraction large, because the reconstruction is easy. So then the initial discovery channel was Higgs to gamma gamma to look for the peak, gamma gamma peak. So sometimes we call it bump hunting. So searching for a bump is always the most rewarding signature if this new physics you are looking for does give you this feature. Okay. If that's not a bump, typically it's harder, but the bump will be the easiest. So finally, the missing particle. What do we do with the missing particle? But we can deduce the existence of the missing particle by the energy momentum conservation. So that's what we have to do. Okay. So finally, for the missing particles. So the missing particles, in principle, we know that the initial particle P1, initial particle P2 to decay or to produce the final state particles, then this the P1 plus P2 equal to P sum over final state, right? So that's the momentum conservation for when we do the phase-based stuff. Then you have a bunch of observable particles, maybe E plus minus or other things, and whatever observable particles momenta, you just add them up. But in principle, there are also some missing ones. Let me use a different color if that can be. So that is the exact relation in the full momentum sense, both in energy and the three momentum. So that is in general. However, the missing particles will not be recorded according to our components there. So it's not directly measurable. Not directly measurable. They are gone. So therefore, there's some mismatch in how to construct these here. In the E plus minus collider, then the initial beam energies and momenta are precisely accurately determined. So that part is known. So initial. However, in the hadronic collision, then the high energy collisions take place into the sub-constituents, partons, the quarks and gluons, and these kind of things are really the direct initial state particles to participate into the reaction, not the measurable, not the experimental setting protons, not the two protons. High energy is really the sub. And these two, so it's not exactly known. It's a very broad spectrum. It depends on the so-called those partons. Depends on by the so-called parton distribution functions that I will discuss a little bit towards the end for the hadron collider part. So that part is not very much known. But that's not very much known only along the proton moving directions. Okay. Protons and partons have very little transverse motion because they are really head-on z direction contributions. Therefore, this formula can be made more useful if we convert these into the transverse. If we make this into a transverse direction, then it's known. It's zero. This proton has no transverse motion. No, it's basically the z direction. And the partons carry very little transverse momentum as well. So therefore, in the hadronic collisions, that part is still true. In the E plus minus, of course, this is also true, right? But E plus minus, even the longitudinal direction is very well known. It's center mass energy. Okay, no. But here, that tells you this relation, this is zero. So therefore, it tells you that the observable particles, you collect them all, will be, okay, so then that will be equal to the missing particles in the transverse direction. So this is the momentum, only momentum, okay. Only momentum in this direction. The transverse component, which basically means x and y, and z part is unknown because of the very broad distribution. And in the transverse direction, if you see the imbalancing, you can deduce the existence of missing particles. So far in the standard model, it's only neutrinos. But so far in anything beyond standard model, it's only neutrinos. We haven't seen so that's what the search for dark matter. This is the primary search for dark matter. So whether there are additional missing particles beyond our standard model stuff. Okay. So is this it's about time? Okay. Let me see if I can. Okay. One more comment. So here is the missing momentum. Let's write this into the transverse sense. But if I write into the vector sense, I mean that's both in x and y directions. X, y directions. Okay. But this is rigorous. But our experimental colleagues, for historical reason, call this missing energy. Okay. In fact, it's not the energy. It's really missing momentum. It's even not the reason they call that missing energy is that the observable momentum, large fraction, happen to be here. Okay. They measure these observable particles, not really measuring the momentum and momentum muon. Significant fraction of the events are not from the chart tracks, rather from the colorimeter. That's why they call it energy. However, they measure the particular point. Once you know the location, you know the magnitude, and you know the components, x component and y components. So they call this energy measurement, and that's missing. They call this missing energy. However, later you will realize that when we do the energy is momentum squared plus mass squared and root. But if even you say this is a missing, if even you say these transverse components, the transverse missing energy is also transverse component of momentum with additional particle mass in it. So the missing energy here, if the missing transverse energy, the transverse energy terminology is only sensible. It's only sensible if the measured objects are essentially massless. If the most of the time is true, quarks, photons, electrons, most of the time is true. We haven't seen the untrue yet, but I will give you example untrue for beyond standard model new particles. Most of the particles measured in that the detector components would have a massless particle. Therefore, the momentum magnitude is same as the energy magnitude. You call this missing energy by the momentum. That's numerically okay, but conceptually different. Energy is not a vector. Energy is a number. Energy has no transverse issue, but it's borrowed from our momentum language. So that's okay. We can people can use that. But the real measurements is really from the momentum. But only in the massless case that a momentum component can be associated, can be identified as an energy component, which is okay. So far there's nothing wrong, but it's confusing, somewhat confusing. So that's it. Okay, so I think it's a time. So we stop here, and next time I have to squeeze in both E plus minus features and the hadronic collider features. Okay, thank you.